Well, good morning, one and all. Our attempt today is going to be finish chapter, whatever we're on. Try to do most of the next chapter. Is it 29? We were talking about this just now, weren't we? Finish 29. Try to get as much to 30 under our belt as possible so that we have time for 31 and 32. This week is a normal week, and then next week we meet on Monday and Tuesday. Because we don't have class on Wednesday, right? I mean, normally we don't have class on Wednesday. So, but yeah, there's no Thursday, no Friday because of the Thanksgiving holiday. All right. Up till now, we've established that light and electrons and basically everything can be a wave, can be a particle. It just sort of depends on what scale we're looking at and what it's doing. And so physicists attempted to come to grips with this new reality, this wave-particle duality, and to describe something that is both a wave and a particle gets pretty hairy pretty fast, okay? So this is a lie. It's a good lie. But this is a model or a framework that physicists use to be able to try to come to grips with what's going on here. This picture that I'm showing you is both a wave and a particle. So if your brain needs something concrete to sort of latch onto, this might be it, okay? Notice, does this thing have wavelength? Yeah. Does it have frequency? Yeah, it's got all of those features that a wave would have, right? While simultaneously being confined to a specific region of space, right? This wavy thing has a beginning and an end. I always think of it kind of like a football, right? It's got sort of like, it looks like it has an envelope of sorts that contains this wave. So it has both wave properties and particle properties, because particles, take up a certain location and amount of space, that sort of thing. But that's a gross oversimplification of what's going on here. Because if we treat things, all things like this, light, matter, doesn't matter, we end up in a situation where we can't precisely know exactly what's going on. And in order to sort of express how things can be both particles and waves at the same time, we have to give up a little bit of our kind of classical idea that we can always know everything about anything. This is a very Newtonian idea. Basically, just tell me what the initial conditions of the universe is and I can tell you everything about anything for the rest of forever. Turns out that at small scales, the scales of atoms and electrons and neutrons and protons and things like that, that you actually can't know everything about anything. There is a trade-off in the amount of knowledge or things we can know about quantum systems. This was famously described by Werner Heisenberg, okay? The man knew hats. That's all I'm going to say, right? His nose was huge, comically so. He himself pointed it out all the time, but he had style. Werner Heisenberg, just as a side note, was a Nazi and was part of the German nuclear program to build atomic weapons. Werner Heisenberg would later be captured by the Allies, brought over to the United States, and have a distinguished scientific career here in the United States. And there was something wrong with the German atomic weapons program. It should have been very much in front of the American atomic weapons program at the time. They had all of the best scientists in the world that knew about nuclear physics at the time and quantum mechanics. Werner Heisenberg was chief among them, and he was the kind of the scientific head of that aspect of the Nazi regime. And what should have happened is the Germans should have gotten to the atomic bomb first. But they didn't. Werner Heisenberg would never admit to sabotage. But the historical record and several historians are in agreement that without Werner Heisenberg, the Nazi program probably would have been more successful. Records captured after the fact and things that the Allies learned about the Nazi program showed that fundamental mistakes were being made that led the German. So the scientists made mistakes, which led the German politicians to think that nuclear weapons were impossible to make, when in fact, those German scientists knew exactly what they needed to do to make it. And so there's ample sort of circumstantial historical evidence that Werner Heisenberg and others are responsible for convincing the Third Reich that what the Americans were doing was impossible and that the Germans shouldn't put any stock into it. So there's a lot of ambiguity in history, but I find these kinds of things very fascinating, right? So anyway, Werner Heisenberg specified this thing called the Heisenberg uncertainty principle, and I should probably write it down before I start doing some examples of it. But it's like a mathematical statement for the trade-off between knowing kind of where something is located and how fast it's going. Hold on to that sort of idea there. We have to trade between knowing where something is and how fast it's going. I'm going to write it down kind of funny, and then I'll explain just what's going on here, okay? So the deltas you're about to see are not the deltas that you know and love, okay? Sorry about that. It's just the symbology that's been used in quantum mechanics. Okay, about the only thing you might recognize there is the right-hand side, right? We've got Planck's constant, and we've got 4 pi, okay? Generally, in this equation, you'll want to use Planck's constant in the joules times seconds variant, because the p on the left-hand side is momentum. And remember that this momentum is m times v. And so when I say we can't know like how fast it's going, this is always written in terms of momentum, but really momentum is all about how fast something's going. Mass is mass, but the velocity can be different depending on the situation. And then delta x is all about location. In your book, they'll write delta y. It doesn't matter, okay? Delta y, delta x, delta z, just position, some position coordinate. The deltas here are not final minus initial. These are uncertainties. Now, Werner Heisenberg wrote down his papers and all of his mathematics and all of his language in German. And if Germans do something right, it's they invent really good words, okay? Like they will just mash together as many like syllables as they possibly can into one word, right? And end up with a town name that, like, they'll say in German, they'll say something like the town where the cow died in the well and 30,000 people died on the 5th Tuesday in March. And it'll just be all one big long word, right, to describe this town, okay? Well, Werner Heisenberg, being the good German that he was, used a German word to describe this principle that was subsequently translated incorrectly, or at least doesn't have a exact term in English, okay? So when people read uncertainty principle, they're like, ah, physicists are not certain about anything, we can ignore them. Fair, right? But not true, okay? The word that Heisenberg used is probably best translated into English as unknowability. That's not really an English word that we have, right? We understand it if we understand how prefixes and suffixes work in English, but like we don't have a word like that. Okay? So this is really all about the Heisenberg unknowability principle. You can't know 100% about something without losing a lot of information about something else. And what we're trading is knowledge about where things are and how fast they're going. So, for example, if I am measuring an electron, I say that electron is right there. Like I'm 100% certain in my measurement. Like I know it's right there. then I am 100% uncertain as to its velocity, its momentum. I don't know where it's coming from. I don't know where it's going. I don't know anything about how fast it's going. I don't know anything about the direction it came from, because I know with 100% certainty where it is. Now, if I kind of look at this 1 meter right here, I say, well, my electron is somewhere in here, okay? And I'm like 50% sure I know that it's in this location. Then I gain some information about where it's coming from and where it's going. I can be 50% sure about its velocity. So that's what the Heisenberg uncertainty principle tries to capture. But more fundamentally, it teaches us that in quantum systems, in systems where the wavelength matters, right, where things are small enough, we can't know exactly where electrons are. And so electrons aren't these particles with definite information. They're these waves with loosey-goosey information. We're not quite sure exactly where it is and what it's doing, but we have some predictive ability there. So how do you calculate things with the Heisenberg uncertainty principle? I'll do an example, right? But just so you remember, these deltas, right? Those are like percentage things, and I'll show you what I mean by that. They're not final minus initial. There's another variant of this that works for energy and time. And you might see examples of it in the book or on YouTube or whatever, right? Where people are doing it this way. It's just same idea. Instead of position and velocity, it's energy and time. You can't know the absolute energy of something without losing all of its temporal information. You'll also see sort of variants of this where they'll do something like they'll just say H sometimes. Sometimes they'll do H bar. I'm just kind of letting you know, right? Because of how the internet is, there's different sort of statistical ways to approach this. H bar, by the way, is shorthand for Planck's constant divided by 2 pi. Physicists got tired of dividing by 2 pi all the time, and so we'll write H bar. So you'll see H bar, you'll see H bar over 2. This isn't physicists being uncertain. It's just the difference between all these things is where you choose your origin of coordinates. I don't want to get too far deep into the weeds here, but I just know that you might see different variants. We will use the ones in the boxes on the screen. Well, H bar, H over 2 pi, right? See how I wrote H over 4 pi? Your author technically is doing H bar over 2. There's a schism in physics between should it be H bar over 2 or H bar. And this is the same argument as, well, where is 0? If we put 0 over there, then all this information is positive. But if we put 0 over there, all this location is negative. It's just an origin of coordinates issue, whether or not there's a factor of 2. But the reason for H over 2 pi is because 2 pi shows up in quantum mechanics all the time. So we don't do H over 4 pi, 2 pi, because 2 pi is the ordinate. That happens all the time. Anyway, how do we go about doing this, okay? So here's an example of working with the Heisenberg uncertainty principle. Again, the calculations themselves are not difficult. It's getting all the pieces in the right order in the right place. That can be troublesome. I was going to say would lead to uncertainty, but that would be a really, really bad pun. No. Okay, so what do we got? 35 meters per second. So here's a mass and here's a velocity, and that's a momentum, isn't it? Okay, so let's go ahead and let's just calculate right away the momentum of this volleyball, right? We'll do part A first. So the momentum, mass times velocity, is going to be 0.35 kilograms times 35 meters per second. It's going to get me 0.613 kilogram meters. The units of momentum. This is straight up physics 4A stuff, okay? So, oh, sorry, no, that's not the answer. Oh, I went too far. What is 0.35 times 35? It's 12.25. There we go. Went too far. So when we go to calculate delta P for the uncertainty principle, remember the delta isn't final minus initial, it's an uncertainty. What is the uncertainty in the measurement for this momentum? It's 5%. And how do we write 5% as a decimal? 0.05, right? So when we go to calculate this uncertainty, we're going to do 0.05 of 12.25. And that's going to get us the number I gave, 0.613. Sometimes I just write plus or minus on the front of it to remind me that this isn't like the actual momentum. This is like the plus or minus value on the measurement of momentum. Okay? So 5% of the momentum is 0.613. And that is our uncertainty. To figure out what the uncertainty is in position, I'm going to take our h over 4 pi and divide it by our delta p. Right? So this is going to be h over 4 pi times 0.613. And when we calculate this, we get 1.72 times 10 to the minus 34 meters. Okay? What is that trying to tell us? It's not telling us where it is. What that delta x is the plus or minus value. Again, sometimes for me, I sneak in a plus or minus to remind me that this isn't the actual answer for where this volleyball is. What this is the unknowability of where it is, the uncertainty in the measurement that's taken place. In other words, we might say the volleyball is right here, and then the Heisenberg uncertainty principle tells us that we know that to within plus or minus 1.72 times 10 to the minus 34 meters. Now, how big is that uncertainty? It's impossibly small, right? In other words, we know where the volleyball is, okay? Like for sure, right? Because we can't measure down to anything less than 10 to the minus 17 or so meters, right? So there's no possible way for us to say, wow, it's kind of there. No, we know exactly where this volleyball is, and that's okay. I mean, that's normal. Everyday objects, right? Like the eraser, the trash can, whatever, right? We know exactly where these things are. There's no uncertainty in where this thing is, right? Okay, it's because this isn't a quantum system. It's too big, right? And it's not moving and all kinds of stuff. So rest assured that you don't have to worry about where things are or not, okay? For large everyday objects that we interact with, it's not that big a deal. So let's do the other side of the coin here where we do an electron, right? This is where things become less certain. No, this is very bad, right? Let's calculate the uncertainty in the momentum of this electron just kind of straight off the bat. We don't have to calculate the momentum first because we know it's plus or minus 5% again. So we can do 0.05. That's that percentage, right? And I don't know why it's movies. It should be moves. Movies. Maybe it likes the movies. 9.11 times 10 to the minus 31. And it's moving at 35. So the momentum, right, this is P, and this is the delta, right? So I'm just kind of doing them together this time. So when I did that, I got plus or minus 1.59 times 10 to the minus 30 kilogram meters per second. And then when I go to calculate the uncertainty in the electron's position, h over 4 pi, and then I put in my 1.59 times 10 to the minus 30. And when I get this out, I get 6.64 times 10 to the minus 5 meters. All right, that's a lot more interesting. First of all, that's 66 microns, which is drop dead easy for us to measure. More importantly, the uncertainty, the plus or minus value about where this electron is approximately 100,000 times bigger than an atom. So as far as an atom is concerned, where's an electron? Anywhere, right? Like, this is kind of the point here, right? 5% certainty on the momentum of an electron. In other words, we know 95% like where it's coming from and where it's going, means that we lose almost all information about where it is. And this is important because we use electrons to do a lot of stuff in our modern technology. And if we lose track of those electrons, if an electron can't be defined inside, say, a circuit for memory, then you've lost that bit of information, which can be catastrophic to your term paper, right? So in our modern technology, we deal with this problem all the time, okay? So we are now, with electrons and neutrons and protons, we're at a scale where this inherent quantum nature of things matters. And we have to deal with it. And deal with it we shall as we move into chapter 30, which is the real quantum mechanics chapter. And so what we're going to do to start dealing with all of this is take a little tiny bit of a historical aside so that you can contextualize exactly what's going on with quantum mechanics and everything that we've been talking about. I got a little ahead of myself talking about the uncertainty principle, but those were all sort of base groundwork things we needed to understand in order to sort of see where modern quantum theory comes about. And by the end of this chapter, which may or may not be today, you will understand everything there is to know about chemistry. Everything. I can do it. I can do it in 2 hours. It takes chemists 2 semesters to do it. Okay? So we're going to back up. We're going to back up, what is this, 1896? 97. J.J. Thomson, a British guy, anger management issues. We don't need to go into that. He ended up destroying a whole lab's worth of glassware because he was upset that he couldn't make things work. Anyway, he is credited with the discovery of the electron. Now, what he measured was something called the charge to mass ratio. But think about it, before 1897, we didn't know electrons existed. We really didn't know atoms were a thing until the 1600s, and then they were just kind of a guess, right? And it wasn't until Einstein wrote the paper on the Brownian motion that everybody was like, yeah, you know what, atoms do exist. This is proof. Okay, so 1897, we're still trying to figure out lots of pieces of the puzzle. The electron's going to be a really important piece of the puzzle. But the other thing that Thomson did is he put forth the first scientific model, published model, of what an atom might look like. And being British and a physicist, he used a food analogy, and it's a British food called plum pudding. You guys ever heard of this model of the atom before? They don't talk about this in chemistry, do they? Some do, some don't, okay? It turns out to be completely flawed and not right, but it's really, really important in the context of, one of the things I want you to learn today is how science continually messes up. We mess up all the time, but as long as we keep pushing and trying and realizing where things are going wrong, in the end, we'll get it right, and you'll see that today. So Thomson, plum pudding is like bread pudding. If anybody's had rice pudding, it's kind of similar. You make sort of a mushy, gooey thing, and then inside of it, there's pieces of fruit or chocolate chips or something, right? Okay. We might be more familiar with a blueberry muffin, right? You've got this muffin, and then inside it, you got the blueberries, right? So this is what Thomson did. He developed this model where an atom was this ball of positively charged goo, and inside the goo were these electrons, right? These little tiny chunks of matter that had, an atom normally would be neutral. The amount of positive goo and the number of electrons would cancel out the charge. You'd have neutral, all that kind of stuff, right? Well, we would later realize that that's wrong. And the way that we figured out that it was wrong is an excellent story in and of itself. Because 1897, Thomson is discovering the electron and putting forth this plum pudding model of the atom. And a year prior to this, a physicist by the name of Henri Becquerel is working in Paris. Now, Henri Becquerel is the absolute model of the scientific method. I can't think of a scientist off the top of my head that failed harder than he did. Like, Becquerel failed at just about every single thing he put his fingers on. Not like failed as in just did it completely wrong and was an idiot, but like he would come up with a hypothesis, he'd test the hypothesis, and it would be wrong, right? So he'd go back and he'd do another hypothesis. Well, it turns out that was like he had a knack for getting the wrong hypothesis, basically. But he always kept at it. Well, in 1896, Becquerel had been, 95, he had been mailed some samples of these interesting rocks from a friend of his down in Romania. And Becquerel's in Paris, and he gets these rocks, and his friend sent them to him saying, I think you'd be interested in these because these rocks have an internal warmth. They're giving off their own heat energy, and nobody understands where it comes from. You might want to take a look at it. So Becquerel, at the time, he's not interested in these warm rocks, and so he puts them on a shelf, and the shelf he puts them on is right next to the cabinet that holds all of his photographic plates. Well, Becquerel was using these photographic plates as a kind of rudimentary X-ray machine. He, again, was doing it all wrong, but what he was doing is he was taking like leaves. Leaves had a bunch of veining structures, and he was trying to get an idea of the mathematical relationship between all the veins and things. So you would take the leaves, and he'd put them on top of one of his photographic plates, and he'd set that out in the sun. And so the sunlight would come down, pass through the leaves, get blocked by certain parts of the leaves, and he'd end up with like a photographic plate of what the structure of the leaf looked like on the inside. Doesn't sound very physics, but like he's trying to see if he can't come up with a way to kind of take pictures of the internal structures of leaves. Again, he's a little bit ahead of himself. This concept would later become known as an X-ray machine, right? And it wouldn't be using visible light, it'd be using X-rays. But like he's kind of on this right track, but again, he's completely like failing at it over and over and over again. Well, he's got all of these plates, he's got them in a cabinet, he sets these rocks next to the cabinet. It turns out that for the next like month or so, it's pretty cloudy in Paris, right? And he only has like a few days of sunshine, and so he's kind of puttering around waiting for the sun to come out. And when the sun finally comes out, he opens his cabinet of photographic plates. And remember, this cabinet is designed to be like really dark inside to keep the plates from being exposed. And so he had all these light controls to make sure that they weren't getting extra light and all this kind of stuff. And he starts pulling the plates out so he can run outside and put his leaves under the sunshine when he notices that several of his plates are already exposed. And so now he's like bummed because he knows he's got a light leak somewhere in his storage system. So he spends a few hours trying to figure out where the light's leaking in from so he can fix this, and all the time the sun's going down and he's getting all upset. And he can't figure out like why these plates have been exposed. They're like foggy. And as he's looking at it, he starts noticing that the plates that are the most exposed are the ones that are sitting next to the shelf with the hot rocks on it. And he starts kind of putting two and two together. It was like kind of the one hypothesis that he really figured out right away. And smart guy, but just like, again, had a knack for choosing the wrong explanation for things. And he's got these rocks in his hands, and he's looking at his cabinet, and he realizes that the plates next to the rocks are the most exposed. He goes, that's weird. And so he takes the rocks, he opens the door, he walks down the hall, about 3 doors, turns right, knocks on the door, and a young woman answers. And he hands these rocks to her, and he says, Marie, I think you and Pierre would be interested in these. Becquerel had just handed Marie Curie her first Nobel Prize. She would take those rocks and with her husband isolate the element that was causing the radioactive decay that Henri Becquerel was detecting in his photographic plates. It would take them 3 to 4 years working together in their laboratory. They would end up getting like radiation poisoning from their efforts to like concentrate and isolate this radioactive element. And they would discover radium, which was the first of the radioactive elements to discover. They would discover the 3 kinds of radiation that we're about to go over, the alpha, beta, and gamma radiation. Marie Curie would become not only the first woman to win a Nobel Prize, but the first person to win 2. She won the Nobel Prize in physics first, I believe, and then later won the Nobel Prize in chemistry for work. So she shared the Nobel Prize with Becquerel and her husband Pierre for the discovery of radioactivity, and then the chemistry prize a few years later for isolations of other radioactive elements besides radon. She would go on to found a college for women, exclusively for women, to study the sciences, particularly physics. She would have an affair with a Paris scientist that was very scandalous. So she was, far from a perfect person, but at the same time, absolutely brilliant in her age and in her life. Her life would be kind of a sad story. To all records and people that knew them, Pierre and Marie were just madly in love with each other. And one fateful day on his way home from the lab, holding a bouquet of flowers for Marie, he would step in front of a carriage and get run over and be dead before they could take him to the hospital. So a tragic end, and Marie really mourned the loss of her husband for many years. So we can't be hard on her at all. Their work in radioactivity would spur another physicist by the name of Ernest Rutherford to begin questioning Thomson's model of the atom. And what Rutherford realized as with radioactivity, with these alpha, beta, and gamma particles, he could actually use one of those particles to try to probe what an atom was like. And Rutherford's experiments involved using gold foils, gold leaf foils. Gold leaf is a very thin material. You can make like aluminum foil, but make it out of gold. But gold, it can hold together and yet be very, very thin. And he needed it to be thin because Rutherford was going to fire alpha particles towards this gold foil. Well, Rutherford actually wasn't he was an okay scientist, but he was a better commander of people. And so he very quickly got bored of doing the experiment himself, and so he started making his graduate students do it. The graduate students' names were Robert Millikan and Hans Geiger. And if you recognize the name Geiger, this is the same Geiger that would later develop the Geiger counter. What does a Geiger counter do? It counts Geigers. No, it detects the presence of radioactive particles, right? The very graduate students that were tasked with, hey, do this hard experiment and count the number of radioactive particles that go through the gold foil. Necessity is the mother of invention, right? So Geiger would sit down and figure out how to make a device that could do the counting for him. So long story short, Geiger, Millikan, and Rutherford discovered something that was completely unexpected. And to describe it to contemporary audiences, Rutherford would do lectures for the public. And he would try to describe how amazing the results of their experiment were. Namely that most of the alpha particles would go through the gold foil, but some of them would bounce off the foil. or get deflected at very strange angles. He said it would be much like having a 16-inch gun. Back in this time, they're ramping up to World War I. Battleships are the big thing, and battleships have these huge guns on their decks. And a 16-inch gun means that's the diameter of the projectile. So the bullet that they're loading into these guns is 16 inches in diameter, roughly that big, right? 100-pound, right? And they put a bunch of powder in there, below, and they could shoot over the horizon kinds of stuff. So he says, imagine I take a 16-inch gun and I point it at your face. And all you have is a tissue to protect yourself. And then imagine, to your amazement, when I fired the gun, that the 16-inch shell would bounce off your handkerchief. That's kind of like what was going on with the gold foil and these alpha particles. The alpha particles should have ripped straight through that gold foil, but they didn't. Many did, but some didn't. Some bounced off this gold foil, which shouldn't have happened at all. And so Rutherford develops a model for the atom. He looks at Thomson's model and says this has got to be wrong, and based on his experimental results, determines that atoms must be made mostly of empty space. But there is a central nucleus or ball where the mass of the atom is concentrated. And it's this central nucleus of material that is causing some of the alpha particles to bounce off the gold foil. Mostly the alpha particles go through, no problem. And they're passing through the empty space that atoms are made up of. But because this central mass is so concentrated, there's a large portion where the alpha particles come in and they rebound off of that nucleus. So Rutherford, right, is the first really to publish about how atoms are mostly empty space. He coins terms like the nucleus and the proton, this particle of positive charge. Later, he realizes there's not enough mass just in the nucleus coming from protons, so there must be something else in there that has mass but no charge. So he coins the phrase neutron, right? You're seeing where a lot of these terms that we still use today are coming from. He's trying to what's a visualization I can use where an atom is most of the mass of the atom is at the center, but the electrons are orbiting or zooming around this center. Is there something in the universe that acts like this, where there's a really heavy center with other things orbiting around the outside? Any ideas? Solar system, right? The sun, 99% of the mass of our solar system in the center, with a lot of things around the outside zooming around it. So he calls this the planetary model. Right? He's modeling this after the solar system, where these electrons are in orbit around the nucleus being positively charged, and the electrons being negatively charged. They're drawn to each other. It's the planetary model, right, of the atom. He coins the term atomic number to describe the number of protons in the nucleus. And this atomic number is going to tell us what the element is. The number of protons in the nucleus of an element tell you that it's hydrogen or helium or boron or argon or whatever element you're looking at, right? That element, its very nature is determined by the number of protons in its nucleus. He calculates the radius of this atom, finds that it's incredibly small, right? And the space between the nucleus and where these electrons are actually orbiting, because he calculates what all the orbits of the electrons need to be, that space is empty space, which he kind of, in my opinion, he got wrong, because obviously what exists between the nucleus of an atom and the electrons in that space is olive oil. Because olive oil, according to us Italians, is what holds the universe together. Right? Olive oil must go on everything. I'm joking, of course, right? But this is the first time in science where an atom is being said to exist of empty space. Like there's nothing in between. And problem is, nature abhors a vacuum, sort of this old idea that we borrowed from the Greeks. And so there's a little bit of disquiet about this, right? So the problem, though, is that if you have electrons going around in circles, that's accelerated motion. By definition, anything moving in a circle is accelerating. It's changing its direction all the time. And one of the things we learned from all of the electricity and magnetism we did is that if you accelerate a charge, it's going to give off energy in the form of electromagnetic waves. That's where electromagnetic waves come from, is charges bouncing up and down. So charge going around in a circle should be giving off its energy. And if the energy is getting less, what should happen to the radius of the orbit? Should also decrease. In other words, based on Rutherford's model, all electrons should spiral down and crash into the nucleus. And if you calculate the time this takes, it's like hundredths of a nanosecond. Like it's really fast, right? I mean, you can look at your thumb. Is it still there? It's still there. I mean, obviously this isn't happening, right? Matter is stable, not unstable. And so Rutherford's model has this problem, okay? Rutherford isn't an idiot. He knows this is a problem, but he can't, like he's just reporting on his experimental results. He's saying this is the model I'm putting forth based on these results. There's issues with it, but I think this is a step in the right direction. He wouldn't be wrong. Now, Rutherford was a little bit of a jerk. He kind of believed in the absolute supremacy of physics being the top science, and all other sciences are just derivatives of physics and blah, 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 right? So when the Nobel Prize would be awarded to Ernest Rutherford. So Ernest Rutherford famously on the record quoted as saying, physics is the only science. All others are stamp collecting. He was referring to chemistry directly. When he was asked about what do you think of the science of chemistry, and he said, well, physics is the chief science, everything else is stamp collecting, meaning that you're just categorizing or collecting information, getting all your Pokemon in order, and that's about it, right? Ernest Rutherford would win the Nobel Prize, not in physics, but in chemistry, for his work on this model. I think that is evidence for the Nobel Prize Committee's understanding that he was a jerk, and they gave him the one prize that he didn't want. He would never get another. Anyway, Ernest Rutherford publishes all this, while simultaneous to all this happening, black body radiation and something we've already seen, which are the spectral lines for gases. Remember when we did when I took the groovy glasses out? I showed you hydrogen, I showed you neon, and there were these fingerprints. So from the 1860s and 70s onward, these had been discovered, and they had been categorized, and even mathematical models had been made to figure out the relationship between all of these different spectral lines and things that are going on. We're going to write down some of this math, but the important thing to know here, right, is that these emission spectra are like the fingerprints of atoms, okay? And you always, for hydrogen, you'll always get these four spectral lines, okay? Mercury, same set of lines. Neon, all of its lines, okay? And these, in the case of hydrogen here, the visible ones, okay, that are sitting right here, okay, all these visible lines, right? Those are known by a mathematical series, okay, called the Balmer series. Now, it's written kind of funky. You just kind of hold on for the ride and just calculate things, okay? But it's written funny. So this is called the Balmer series right here. And there's a constant called the Rydberg constant, which is floating around here in the front, 10 to the 7 inverse meters. I'm going to call this the Balmer series. Balmer was the guy that not discovered the wavelengths, but discovered the mathematical relationship between the wavelengths. Okay? So let me see if I can unpack this for you. Do you see this little n right here? It's a number, it's an integer, 1, 2, 3, 4, 5, but you have to start at 3. Why do you have to start at 3? Because there's a 2 right here. I know it's weird. It'll make more sense in a little bit. Okay? But basically what the Balmer series does is it lets you calculate these wavelengths. Okay? You put n equals 3, you get this one. You put n equals 4, you get this one. N equals 5, you get this one. N equals 6, you get that one. Okay? The 4 visible wavelengths are all sitting right there. Again, Balmer, in coming up with this mathematical relationship between the wavelengths, has just discovered a mathematical relationship. He is unable to explain why this mathematical relationship exists. Okay? The Balmer series would be one of many that would be discovered. Okay? And more generally, in hydrogen, these series can be written as 1 over, like, there's different ways to talk about this. 1 over n1 squared minus 1 over n2 squared, where n2 is always bigger than n1. In other words, if n1 is 1, then n2 can start with 2, but it can't be 1. If n1 is 4, then n2 has to start with 5, right? They're all integers, but the more general version of this would give rise to all the other wavelengths which at the time couldn't be detected. These wavelengths right here are in the ultraviolet portion of the spectrum. Okay? There would be infrared versions of these. Okay? But nobody would know why different elements gave off exactly the same fingerprints all the time and they were unique to that element until Niels Bohr would show up on the scene. So 1912. Bohr is he's got his degree, he's got his doctorate, he's working on atomic theory, quantum mechanics, all this kind of stuff. And he visits Rutherford's lab, okay? And he gets really interested in trying to figure out the answer. Like, why is it that Rutherford's electrons are not giving up their energy? How is it that they are orbiting and not decaying in their orbits? This really starts to fascinate him, and it kind of lodges in his brain. And by 1913, he would have an answer. It would be significant for many reasons. Scientifically, it would be significant because this would be the first time that anyone had used quantum ideas, quantum mechanical ideas, in an atomic model. And so that's probably its biggest claim to fame. But there's something else going on here that you need to realize. And this comes back to the human story and the personal story of Niels Bohr, and especially his relationship with his wife. We don't know what Niels Bohr had, but it was probably an extreme form of dyslexia. He had a problem with his handwriting, especially. Like, he couldn't write things clearly at all. Like, even he couldn't understand what he had just written down on the page. And so for his entire life, he always had scribes. He would go to lectures as an undergrad, as a graduate student. He would go to lectures and he would just sit there and listen. And then he would run home, and his chief scribe kind of in his college years was his mother. And he would dictate to his mother, and she would write down what he told her. Now, she had no training in mathematics, right, or calculus or any of these kinds of things. So Bohr would have to describe the shape to her of an integral and all these different kinds of things. And she learned pretty quickly how to do it, and so it would get faster and faster and faster. But this was how Bohr had to operate. Okay, he just didn't really have a choice. So somebody with this kind of handicap, it would be kind of difficult, right, to get through school and all this kind of thing. Well, birds and the bees, men and women, you know the story. We won't go into that topic, right? But Bohr meets Mrs. Bohr, right? Prior to their marriage, they court each other, right? And she gets involved as being a scribe, right? Being a note taker. Okay, so they get married, and they're planning the honeymoon. And the honeymoon is going to be them leaving by train, and they're going to be gone for a month. The day before they are scheduled to leave on the train, Bohr comes running into the house saying, I figured it out, I figured it out, I figured it out. I have to get this down. And his newlywed, his bride, says, okay, opens the journal, grabs the pen, and is ready. And he tells her, this is going to take 3 days. Guaranteed. But I'm not going to be able to remember it. We've got to get it down now. But we're going to have to delay the honeymoon. They're scheduled to leave. The trunks are packed. Everything's ready to go, right? We are forever indebted to Mrs. Bohr for saying, go. And for 3 days together, she scribing, him describing, right? I want you to know they eventually went on their honeymoon. Okay? It did happen. But because of Mrs. Bohr, we have the first quantum mechanical model of the atom. Bohr would go on and do amazing things, not just as a physicist, but as a human being. He and his son were responsible for smuggling most of the German scientists out of the Third Reich during World War II. His home country of Denmark would be invaded by the Germans, and he and his son would personally row people across the North Sea to meet with British ships to pick up these defecting scientists. Bohr would always be one step ahead of the law, surprisingly, okay, and would never be captured by the Germans or the Third Reich in any of his clandestine operations. But many a scientist owes their life to Niels Bohr and the Underground Railroad that he would establish to get scientists out of Germany. So what was it that Bohr discovered? What was it? Was it what was the thing? And it's this concept and idea of quantum mechanics, of this idea that energy, the energy levels, these orbits and their orbital energies could only be certain energies, and that there wasn't an infinite number of energies that an electron could be in. They, very much like Planck's staircase model, of energy, where it's not a smooth wheelchair ramp of energy, but there were certain energetic chunks that had to happen. Sorry, you guys, I know, wanted to listen to my lecture, but so this quantum idea, right, that electrons can only exist in certain energy levels, and they transition from energy level to energy level, not by jumping through the space between energy levels, but by literally being in one and then being in the next without having gone through the intervening space. This is a really strange idea for the time, okay? And so it comes down to what he did is he ended up quantizing or chunkifying the angular momentum of these electrons. And in the Bohr model of the atom, okay, he defines this thing called the principal quantum number, which to this day is a number that we still use. But he goes and he calculates the energy levels in the hydrogen atom. We refer to the lowest energy level as the ground state. Okay? And in the Bohr model of the atom, those energy levels, all the energy levels, are actually pretty easy to calculate. Okay? Whatever energy level you want, you just take 13.6 electron volts and you divide by the principal quantum number squared. Again, this counting number indicating which energy level you happen to be on. And so here's the first 4 of these principal quantum numbers laid out, and their energy levels. Okay, again, as you divide by n squared, the number is going to get closer and closer to 0. Right? You start big and then kind of get smaller and smaller as you approach 0. And so Bohr is like theorizing and calculating all these energy levels, but he needs some sort of experimental way to figure out what the energies, like how to measure what's going on here. Okay, and so he does that. I wrote the mathematics on the other screen. Okay, and develops this idea, right, where that lowest energy level, the negative 13.6 electron volts, that's the ground state. That's the energy level electrons want to be in when they're sort of left to their own devices and are settled down and don't have any excess energy to do anything with. Okay? However, if you give an electron energy via electricity or light or any other way, it will jump up into one of the higher energy levels. And Bohr refers to this as an excited state. The amount of energy it takes to jump between one level to the next is just the difference in energy levels, right? So whatever negative 13.6 minus 3.4 is, was that like 9 point something? No, 10.2. Thank you. Okay? That amount of energy is what's required to get an electron that might be here to jump up to here. And vice versa. If it's up here and it falls down, that electron has to give up exactly 10.2 electron volts of energy. Well, how are we going to measure this quantum leap, right? How are we going to see it? Well, it's going to come out as a photon. And that photon is going to have energy E equals hf, a la Einstein-Planck relationship. And that frequency is going to correspond to a wavelength, which is going to correspond to a color, the exact colors of the Balmer series. So what Bohr is able to do is not only use quantum mechanics for the first time, but he is able to explain why the Balmer series exists. All of the colors in the Balmer series are happening because electrons are transitioning from high energy levels to the second energy level in the hydrogen atom. And then he predicted that there was going to be more. And so people went and started looking for more, and they found them. The Lyman series, okay, named after its discoverer, are all the electron transitions from excited states that terminate at the ground state or the first energy level of a hydrogen atom. They all happen to be higher energy, and so they are in the ultraviolet portion of the spectrum. You need an ultraviolet detector to be able to detect those. And they did. They went and they built ultraviolet detectors and they found them. The Passion series, notice the spelling, it's not like passion as in I'm very passionate about this, right? But the Passion series are all the ones that start at a high energy level and terminate at energy level number 3, okay? So that's why, like, when we wrote down this, the Balmer series, you remember? It was 1 over 2 squared minus 1 over n squared is kind of how Balmer originally wrote it. He wrote 1 over 4, but then later realized, like with Bohr's stuff and all the other series, which is why we now write this thing, right, as 1 over, I should have used final and initial notations, right, to begin with, right? And then Bohr would discover that this Rydberg constant, which was experimentally measured, exactly equaled his energy level model for the hydrogen atom that he developed via quantum mechanics, which was, again, just sort of icing on the cake for Bohr is completely on the right track. Now, the problems, so the Bohr model has problems, okay? But it's a step, again, in the right direction. In fact, the Bohr model is still taught. I'm teaching it to you. I'm showing you the mathematics of it. You can do the mathematics of the Bohr model. It's still taught and used in Chem 1A, right? Chem 3A. It's a good model. It's easy to work with. The problem is it only explains hydrogen. And how many elements are there to understand in the universe? Well, I think we're up to 118 now. Okay? So we're 1 for 118. That's the bad news. Good news, hydrogen makes up 99% of the universe. Right? So we got 99% of the universe, locked down. Bad news, the stuff that's interesting is not hydrogen. Like the parts that make you and me us, right? What is it? We're mostly, was it nitrogen, oxygen, phosphorus, and carbon, something like, yeah, right? Okay. None of those are hydrogen, right? Okay. So like the interesting bits, okay, still need to be understood, right? Bohr's model is unable to explain reasons for why things are the way they are, and it can't explain this quantum jump, like the mechanics of it, like what's actually going on. How are electrons moving from one energy level to another, one orbit to another, and not transitioning the space in between? It's impossible. So there's problems. But it is, again, a step in the right direction. Which leads us to the Schrödinger equation. Yes. Okay. And there's all kinds of jokes and things. I mean, I'm wearing my shirt, okay, about the cat being dead. The problem is you can't read the back of the shirt. Right? Okay. So what the heck is going on? So time rolls on. Bohr's got his stuff in 1950. And of course, Albert Einstein becomes famous in 1919. General relativity, all this kind of stuff. Quantum mechanics is kind of born in Louis de Broglie in the 1920s. There's all of this is happening like simultaneously. I've told you so many historical stories, right? But they're really kind of all happening at the same time. It was the time for relativity. It was the time for quantum mechanics. If it wasn't Einstein and Bohr, it would have been somebody else in a few years. Okay? The Marie Curie with all of the stuff that she did for radiation. It's all kind of coming together. And it comes together eventually in something that, quite frankly, physicists really didn't want to do. This is a joke. I've seen this on a t-shirt and other places, right? But quantum mechanics, as we understand it today, has a lot of problems. They are not scientific problems per se. They are problems of a human type. But what I mean by that, okay, first of all, physicists in general nature are pretty lazy people. Okay? We'll work really hard to do like as little math as possible. Okay? We'll do a lot of conceptual heavy lifting and try and explain away that some physicists like math, but we consider them weird. Okay? Most physicists are like, we want simple, basic explanations of what's going on, right? Quantum mechanics is not simple nor basic. Okay? Quantum mechanics, there's no intuition that is going to save you. Niels Bohr said that a person, upon first being taught about quantum mechanics, who wasn't immediately upset and enraged at what they had just heard, did not understand a word that they had heard. Like, the response to quantum mechanics should be outrage. It can't possibly be like this. But the problem is quantum mechanics is our best description of reality, period. Like, experiment and theory agree down to the, like, when you think about percent error, right? And usually, like in labs, we're kind of happy with Newton's laws if we have less than 5% error. If you're using really good equipment, tenths to maybe hundredths of a percent error. Quantum mechanics agrees between theory and experiment to like millions to billions of a percent error. It is by far and away our most accurate description of how the universe works. And we're talking relativity, we're talking Newton's laws, we're talking Maxwell's equations. None of it begins to approach how well we can predict what's going on between observation and experiment and our mathematics than we can with quantum mechanics. There are many physicists, me included, who would wish that quantum mechanics would go away. But we simply can't get it to go away because it works too darn well. There's some physicists like Dr. Kerfoot who likes it, but he's kind of weird. No, actually, I'm kind of the outsider here, right? Many physicists really like quantum mechanics. It's something that works really well. It's got a lot of hard math in it, which some physicists like. Again, head. But like, this is hard. We're going to do the very, very top level of this, right? Because you're looking at spherical harmonics in 3 dimensions. This is really bad, okay? But what the heck is going on? The Schrodinger model, Erwin Schrodinger, I think I have a picture of Erwin Schrodinger. Where did he go? No, I got rid of Schrodinger's picture. Anyway, okay, which is too bad because he wore bow ties, and bow ties are cool. But Schrodinger came up with an idea of how to fix Bohr's problem of these electrons kind of jumping between energy levels. He said, well, let's just take a page out of Louis de Broglie's book. Electrons aren't particles at all. What are they? They're waves. And what happens if you apply wave theory to Bohr's model and the waves are electrons? This is what happens. Basically what happens is electrons are no longer particles that are in orbit around the nucleus. They're more of a fog of uncertainty, a fog that we don't know exactly where they are. They're doing their wave thing. We don't know exactly their positions. We don't know exactly their momentums, but we can kind of statistically analyze what's going on. And that's what he does, right? He comes up with these plots that are the probability of finding an electron at any one location. The probability maximizes is something called the Bohr radius, which is exactly lined up with Bohr's model. If you take that probability and map it in 3-dimensional space, you get kind of this fog where the density of the fog represents the likelihood for detecting an electron at any one point in time. These are some of the equations. These are just the radial solutions. There's 3 dimensions here. This is only the radial dimension. And as you can see, it gets really bad really fast. I don't need you to understand any of these equations, okay? But I want to point out to you that there is something going on here very important. Do you see how these equations have 2 numbers attached to their subscripts? And it kind of goes, 1, 0, 2, 1, 2, 0, right? 3, 2, 3, 1, 3, 0. There's a bit of a pattern emerging here, okay? This pattern is going to line up with something that is going to become what we call an orbital. Now, how many of you have studied orbitals in chemistry class? Yeah, okay. If you've been to chemistry, you know what's coming, okay? What I just showed you, all of this math right here that's predicted from that right there, okay? This is just one of 3 dimensions that you get, okay? These radial solutions will correspond to the orbital types. What's an orbital? It's a 3-dimensional structure within which we can find an electron 90% of the time. 90% of the time, We know that an electron is going to be somewhere inside that sphere for the lowest energy state in the hydrogen atom. You'll notice here that we are not being specific. We're not saying 100% of the time. We're saying 90% of the time. The other 10% of the time, where's the electron? No. Don't know. Can't even be bothered to care to know. It's a question that can't be answered, so why bother, right? Now, notice we're not saying where exactly is the electron. Don't know that either. We just know that 90% of the time it's going to be located somewhere inside that sphere. The probability cloud looks like this. The probability clouds are confusing, so we take a step back and we say, well, just somewhere inside of this sphere is the 90% probability that we will be finding the electrons, okay? And as you start calculating out what these different allowed, basically what they are is standing wave patterns, okay, for electrons in these atoms. Those are the Balrogs, by the way, that inhabit our HVAC system. And there's a pressure when it goes from like turning on and off, all the ductwork goes crazy. New buildings, fantastic. These orbitals, they are predicted by Schrodinger's equation, and all of the solutions that start falling out of Schrodinger's equation. The first two solutions happen to be spherical. They have spherical symmetry, and so they look like basketballs. Okay? But after that, I say it before, I'll say it again. Who needs drugs when you've got physics? Right? Because these shapes are getting nuts. What the heck happened right here? I mean, seriously, right? It's like somebody took a bow tie and impaled two donuts with it. I don't understand what's going on, right? But these shapes are predicted by Schrodinger's equation and are the shapes that tell you that 90% of the time an electron is going to be found somewhere within that shape. In all these orbital pictures, the nucleus is at the very center of the three axes. And so let's take a look at the bow ties there on the second row, these kind of yellowish green ones, right? Notice how there's three that are oriented, like one's along the x, one's along the y, and one's along the z axis. But the probability is 0 at the nucleus, but it gets bigger sort of out in these lobes, right? So the basketballs are referred to because most of the scientists working on this at the time were German. Schrodinger was German. They refer to the first one as the S-type orbital. S is in Sam. And then they go P-type for that second sort of bow tie-ish looking one. The red flowers would be the D-types. And these purple one here would be the F-types. Those happen to be the first letter of the first four German counting numbers. SPDF. After F, they kind of gave up and they just go with the alphabet. So after F comes G, then we're back in kindergarten now. A, B, C, D, E, F, G, H, I, J, right? Skipping S and P, right? So, because those are already been used up. Point is, right? Quantum mechanics predicts where we can find these electrons, and by golly, that's where we find the electrons 90% of the time, okay? In truth, these orbitals overlap themselves in space and time, all centering on the nucleus, and so you can have several of these orbital states all overlapping, and electrons can be in any number of them, okay? Ground state being the 1s, but then going on further from that. I think, yeah, we got a little bit more to go here because there's some other weirdness that falls out of quantum mechanics. But I think what I'm going to do is I'm going to save that for tomorrow. I've filled your brain enough so that tomorrow what we're going to do is we're going to pick up with Schrodinger's equation and we're going to talk about all the quantum numbers and quantum addresses for things. And then we'll actually finish chapter 30 tomorrow, no problem. And I might get started on chapter 31 because we are going back to Marie and Pierre. Okay? There's a lot of nuclear physics that has to happen. We'll get out of quantum mechanics and we'll get back to Marie's story and her incredible genius. next time. I will see you then.